Hi children, welcome to today's class. Do you remember what we studied in the previous class? We were discussing about the work done during the compression of an ideal gas against the external pressure. The gas is getting compressed when we are applying an external pressure which is greater than this internal pressure. That is the pressure applied by the gas. Internal pressure is the pressure applied by the gas. Okay. So this external pressure should be greater than this internal pressure. Then only we can compress this gas. Okay. Now what will be the work done during the compression of that gas that we have studied. Now this compression of gas can be achieved in a single step. That means the piston can be moved from this distance to this distance in a single step. And such process can be called as irreversible process. And the work done during that irreversible compression of gas will be equal to minus Px into delta V, where delta V is the change in volume produced due to the movement of piston. Now, if this compression of gas is taking place in a finite number of steps, in a different number of steps, the total work done will be equal to the sum of minus Px into delta V. Here delta V represents the change in volume in each step. Okay. Now suppose the piston is moving from this distance to this distance in infinite number of steps. That means the piston is moving very slowly. So the total movement of piston from this distance to this distance, that will include an infinite number of steps. Okay. And such a process which is taking place very slowly in infinite number of steps can be called as a reversible process. So now we can study what will be the work done during the reversible compression of the gas. That work done we can represent as W reverse. That means the work done during the reversible compression of the gas. Now suppose the piston is moving in an infinite number of small steps. Okay. So at that condition, the external pressure P external will be greater than the internal pressure by a small amount that we can represent as dP. Okay. So in each small step, the external pressure will be greater than the internal pressure by a small amount dP. So we can write P external will be equal to P internal plus dP. Okay. So in each step, this much amount of pressure is applied on this piston. As a result, it produces a change in volume. There will be a small change in volume that we can write dV. Okay. So like this, many number of steps will be there to reach up to this much distance. Already we have studied in the case of irreversible compression, the work done W is equal to minus Pex into delta V, where Pex is the external pressure and delta V is the change in volume due to this external pressure. Isn't it? In the case of this reversible process, this compression is taking place in many number of small steps. Okay. So the work done in a single step, in a single small step, we can write equal to dW. The small work done in a small step, that we can write equal to dW, that will be equal to minus Pex into dV. That produces a small change in volume dV, isn't it? Then what is Pex in a small step? That will be equal to P internal plus dP. So here we can write dW will be equal to minus P internal plus dP into dV, isn't it? So this is the work done in a small single step. And to find out the total work done during the whole process, we have to use another mathematical operation that is known as integration. Okay. So this is the work done, small work done in a small simple step. To get the total work done, we have to do integration. That is another mathematical operation. So the total work done W reversible will be equal to integral. Okay, integral. In this total work done, the volume is changing from Vi to Vf, isn't it? The initial volume is Vi and final volume is Vf. So there will be a change in volume from Vi to Vf. Okay, so the total work done is the integral of VI to VF minus P internal plus dP into dV. Okay, we are just substituting the value here. And that will be equal to integral VI to VF minus P internal into dV minus dP into dV. We are multiplying these two terms with dV. So we will get like this. Okay. Now dP is the small change in pressure and dV is the small change in volume. Both are very small quantities, so their product also will be very small. So we can neglect this term. So W reversible will be equal to integral VI to VF minus P internal into dV. W reversible will be equal to integral VI to VF minus P internal into dV. Where this P internal represents the pressure applied by this gas. Here we have taken ideal gas inside the cylinder, isn't it? Then for ideal gas we have studied that PV is equal to nRT. Then from this what will be P? P will be equal to nRT by V. So in this equation, instead of this P internal, we can substitute this value P is equal to nRT by V. So what we will get? W reversible will be equal to integral VI to VF minus nRT dV by V. This V we are writing along with this dV. Okay. Now N and R is a constant, and for isothermal process T also will be constant. So these three terms we can take outside. Okay. So we will get minus nRT integral VI to VF dV by V. Now the integral dV by V from VI to VF will be equal to natural log VF minus natural log VI. That we can write like this, minus nRT ln VF minus ln VI. Okay, when we are integrating this dV by V from the lower limit Vi to upper limit Vf, we will get minus nRT ln Vf minus ln Vi. This ln represents natural log. Okay, now this we can write like this, nRT ln Vf by Vi. Okay, so to convert this natural log into log to the base 10, we have to multiply with a constant, that is 2.303. So the equation we can write like this, W reversible will be equal to 2 minus sign is here, minus 2.303, then nRT, then log to the base 10 Vf divided by Vi. So W reversible will be equal to minus 2.303 nRT log Vf by Vi. This is the work done during a reversible compression of a gas. Okay. Now here we have studied that if you are applying an external pressure which is greater than the internal pressure applied by the gas will get compressed, isn't it? The volume occupied by the gas will decrease. But if internal pressure is greater than external pressure, what will happen to this gas? It will expand. Okay, the piston will move outward. That means the gas is expanding its volume. If external pressure is greater than internal pressure, compression will take place, and if internal pressure is greater than external pressure, expansion will take place. Whatever may be that, the work done will be same. That is, work done is equal to minus P Ex into delta V. But the sign will be different. During compression, work is done on the system, that is on the gas. So the work done should have a positive value. And during extend, the work is done by the system. System is applying a pressure on the piston. As a result, this work is done by the system. So that work done should have a negative sign, negative value. Is it clear? That only you have to study here. Now, sometimes the expansion of the gas is taking place against vacuum. Vacuum means nothing will be there. Okay, no medium is present. As a result, the external pressure will be 0. Here nothing will be there, no gas, solid, liquid. So the external pressure on this piston will be 0. So in such case, if gas is expanding against vacuum, that expansion can be called as free expansion. Okay. So in such a case, what will be the work done? W is equal to, already we have studied the formula, minus Pex into delta V. Free expansion means expansion against vacuum. That means outside the cylinder, no medium is present. Okay. So outside the cylinder, no pressure will be there. That means P external will be 0. Pex will be 0. So what will be the work done? 0 into delta V, that will be equal to 0. So if during free expansions, the total work done will be 0. Now we can consider some special conditions. For example, consider the isothermal free expansion of a gas. Isothermal means the temperature remains same. That is, delta T should be 0. The change in temperature will be 0, isn't it? And if there is no change in temperature, the internal energy change also will be 0. There will not be change in internal energy, isn't it? That means the change in internal energy will be 0. So we can write delta T will be 0 for isothermal process, and as a result delta U also will be 0. Then free expansion means the expansion against vacuum. Vacuum means outside the cylinder, outside the system, there won't be any medium. So external pressure will be 0. So W, that is equal to minus P external into delta V. For free expansion, minus P external will be 0. So W will be 0. 0 into delta V, 0, isn't it? So according to first law of thermodynamics, we know that change in internal energy is equal to Q plus W. Delta U, change in internal energy is 0 for isothermal process. So we can write 0 is equal to Q plus 0. So what will be Q? Q also will be 0. Okay. Next we can consider isothermal reversible change. Okay, isothermal means again we know that delta T will be 0. As a result, delta U also will be 0. If there is no change in temperature, internal energy will not be changed. That means change in internal energy, delta U also will be 0. And for reversible process, what is the work done? Work done is equal to minus 2.303 nRT log Vf minus Vl. Vf is the final volume and Vi is the initial volume, isn't it? This is the work done for a reversible process. So first law of thermodynamics, we know that delta U is equal to Q plus W, and delta U is 0. So we can write 0 is equal to Q plus W, or Q is equal to minus W. And what is W here? Minus 2.303 nRT log Vf by Vi. That value we can write here. So Q will be equal to minus into this minus, that will become positive. Positive 2.303 nRT log Vf by Va. Okay. For an isothermal reversible process, the heat transfer will be equal to work done. Okay. Now we can consider isothermal irreversible process. Again, isothermal means delta T will be 0. Delta T 0 means delta U also will be 0. Irreversible process means that is taking place in a single step. A rapid reaction is taking place, or a rapid change is taking place. Okay, so what will be the work done? Work done is equal to minus Pex into delta V. That is the work done, isn't it? So first law of thermodynamics, we can write delta U is equal to Q plus W. And here delta U is 0 for isothermal process. So we can write 0 is equal to Q plus W. Okay. Now Q will be equal to minus W. And what is the value of W here? Minus Pex into delta V. So this minus into this minus will become positive. So Q will be equal to Pex into delta V. Okay. So for an isothermal irreversible process, the heat transfer will be equal to minus work done. Okay. Now the next one is adiabatic change. In adiabatic change, we know that Q is equal to 0. That means no heat transfer occurring between system and surroundings. That can be called as an adiabatic process, isn't it? Q will be 0. Now first law of thermodynamics, delta U is equal to Q plus W. Here Q is equal to 0. So we can write delta U is equal to 0 plus W. Here the work done is known as adiabatic work. So we can write WAD. So for an adiabatic change, we can write delta U is equal to W add. That means adiabatic work. Is it clear? That already we have studied. Using first law of thermodynamics, we have find out the important relationship between work done and heat transfer under some specific conditions like isothermal free expansion, isothermal reversible, isothermal irreversible and adiabatic processes. Okay.